Any more lurking outside? Rightio. Okay, ladies and gentlemen, good evening. Welcome to the Geological Society of London and to this, the 9th Shell lecture for 2012, entitled Geological Aspects of Renewable Energy. My name is David Shilston. I'm the president of the Society. And it's my pleasure to thank Shell for making this series of public lectures possible. Moving to a lower carbon energy system and over time displacing fossil fuels and renewable energy will involve considerable challenges for geologists. Below ground geothermal energy is an obvious example. Deep, high-grade energy for converting to power, low-grade energy for space heating, and shallow for seasonal storage and heat pumping. There is also the challenge of matching renewables' intermittent supply with the patterns of demand. Underground energy storage, such as storing hydrogen in salt caverns, may be a more effective way than batteries. The siting of renewable energy projects from hydroelectric, wind storage farms is also based fundamentally on geological conditions. Finally, finding the new resources needed to manufacture such things as solar panels will create fresh demands, extending across the entire periodic table and requiring geologists to do it. Speaking to us today is geologist Bruce Levell. Bruce graduated from Oxford University in 1978. He has worked for Shell for 32 years on operational assignments in Malaysia, Houston, London, Oman. From 2003 to 2008, he was responsible for Shell's Global Exploration New Ventures. In 2008, he was appointed Chief Scientist for Geology for Royal Dutch Shell, and in 2009, Vice President for Emerging Technologies. And from our perspective, most importantly, in 2009, he was awarded the Silver Medal, the highest honour of the Petroleum Group of the Geological Society. Ladies and gentlemen, please welcome Bruce Levell.
Good evening, ladies and gentlemen, and thank you for coming in for this evening's lecture, and thanks for that introduction, David. It's an honour to be here. I always like coming to the Geological Society. It combines two things that I'm trying to do in the company. One is represent geology as a science within Shell, and the other is look at ways in which emerging technologies, in particular emerging technologies in the renewables domain, will interact with the fossil fuel system and enable the move towards a more sustainable energy system. So it's kind of two passions put together: future energy and renewables and geology. And the theme of the talk is actually the integration, the depth of integration in the energy system and the need for systems thinking, and the difficulty in approaching that problem issue by issue. So the topics, the energy system integration is where we'll start. We'll look at renewables breaking through, and I want to emphasize that given the scale of the energy system, we're talking about breaking through of technologies which essentially exist, rather than looking for new technologies which are breakthrough technologies, because we need solutions in the shorter term rather than the longer term. I'll talk a bit about subsurface energy resources, in particular geothermal. I'll look at subsurface storage of energy and subsurface storage of CO2, and I'll look at the resources which are needed to supply renewable technologies, and a short word on the siting of renewable energy, in particular offshore wind. So this is the shock and awe diagram, and there will be a test at the end. So the point of this diagram is that the energy system is complex and integrated. So we can take one solution or one problem, like the tar sands, for example, but actually we have to look at that in the context of the entire system. This is a diagram of the energy system roughly today. There's about 450 exajoules of energy per year flowing across this diagram. On the left-hand side, you have the sources of energy. Well, As we're all taught in school, energy is neither created nor destroyed, so actually they're all conversions of energy. And on the right-hand side, we have the services, which is what we get out of the energy, so kilometers driven or degree days of warmth for space heating or electricity, so on. And the diagram has been made in such a way, it's a bit like the London Underground map. It's been made such that as many lines are straight and horizontal as possible. So what we've done is we've lined up the fossil sources in brown at the top left, and those mostly go to transport, and then some obviously, or a lot obviously, into power. And then the renewable sources are in green at the bottom, and they go at the moment to things like heating, cooking, food, water. This is a total energy system, and it's for economies which are not only first world economies. And then at the bottom, you've got storage, which is a relatively small aspect of this diagram. Now, if we want to build an energy system which is sustainable and low carbon, and that means low carbon, then it has to change. And this is a diagram set up in the same way, which shows the same energy system in 2050 in a scenario that would meet an emission of 450 ppm CO2 to the atmosphere. In this energy system, there's about 550, 600 exajoules flowing around. And in order to satisfy the population in 2050 and rising standards of welfare and income around the world, this scenario has implicit 40% energy savings compared with today's system. So it's an extreme efficient energy system. That being said, what you see is a change in the energy system. So the arrows in green have got bigger. The arrows are more or less to scale. So they showed a number of exajoules moving around in three categories: thick, medium and thin. The arrows in orange have stayed the same in absolute numbers, and the arrows in red have got less. And what you see is that it's still extremely integrated. In fact, it's more integrated. There's much more choice for the end consumer, and that's thanks to electrification, which is a necessary part of this system. And so the consumer gets to choose whether they use electricity for transport, for example. There's a much bigger need for storage because the renewable supplies are intermittent. So we think of wind and PV, but also biomass is seasonal. So there's an intermittency in the supply which requires a storage need. And the point I want to leave this diagram on is the fact that a change in one part of the system almost necessarily involves a change in another part in the system, and that'll be a bit the theme of the talk. Okay, so the good news is that despite opinion to the contrary, renewables have actually changed from being a science project to being a large-scale industry. So what you see here is the funding stream into renewable energy over the decades from 1970 to the present day. There was an early phase where the industry didn't exist, but there was quite a lot of R&D funding going into technologies which needed to be breakthrough technologies, so increasing the yield of PV systems, for example, photovoltaic systems. So you have, back in the day of Jimmy Carter, solar PV panels being put on the roof as a demonstration to the American people that this was a new technology that they needed to get going after, harness the innovation of the United States. Ronald Reagan took them off again. But the good news is that the mullahs in Germany have put them back on again, massively. So now we've seen a spread of PV panels all over Germany, and as a result of the growth of PV and wind over the last decade, and it's been double-digit growth, the size of the renewable energy industry is now an investment of about $250 billion a year. Now that's a big number. But if I put it to scale with my own industry, so the oil and gas industry, the upstream portion, so exploration and production, that industry spends 450 billion. So the renewables industry is more than half the size of the oil and gas, the capital intensive part of the oil and gas industry, upstream of the refineries and the chemical plants. So an apples and oranges comparison, but it gives a scale. Now that's crept up on us over the last decade, and I think it's a major surprise to most people. It's a leading indicator because you build factories to build turbines or to build PV. The implementation or the deployment of that technology comes a bit later. So the investment is up front. So it's not surprising that the delivery in terms of the energy system is still lagging a little bit. So here you can see that delivery. Renewables at the moment are around 6% of the global energy mix. And the bad news is that includes about 3%, which is hydro, which was kind of there before. So the new renewables are really in the single percents. But it is growing, and it's growing fast. I say double-digit growth in those two areas of solar and wind, in particular solar. And 54% new built power generating capacity in 2011 was renewable capacity. So the build out of those technologies is happening fast. Now, if we come now from that background to geology and renewables, it's logical to start with geothermal energy. So a little short introduction on geothermal energy. The figure on the top left, the left-hand side, shows the conductivity of rocks. And it shows 2 points. One is that the conductivity of rocks is very variable. And that's due to the fact that a sandstone or a limestone has pore space, and that pore space contains is variable between sort of 0 and 40%. And that contains water, typically, which has a different conductivity. So there's a big variability. And then there's the shale component or the mudstone component in rocks. So there are compound mixtures with different porosities. So a wide variety of conductivities, which means understanding heat flow in the earth and where you might drill for geothermal energy is not straightforward. You need to understand the layering. You need to understand the conductivity model. Second point is that water has a very low conductivity, which means that if you put heat in water, it generally stays there. So the conductivity is low. Heat capacity is nice and high. So water is a good means of holding heat, and we'll come back to that. So where does geothermal energy come from? Well, it comes from heat sources within the earth. So that's the stored temperature from the accretion of the earth, the gravitational energy from the accretion of the earth, and in large measure, heat as a byproduct of radioactive decay of the minerals which constitute the earth. And that heat makes its way to the surface via conduction, convection in the inner part of the earth, and then conduction in the outer boundary layer. Unfortunately, the heat flux at the surface is about 50 milliwatts per square meter. It's a good number, which is about 3 orders of magnitude, 2.5, less than it needs to be an energy source. So we typically want a couple of watts per meter to be an energy source at the speed at which we consume energy. So geothermal energy is essentially not sustainable. You mine it. The planet is not going to replenish it in time, but there's plenty of it to mine. So how does it come to the surface? Why in some places rather than others? Well, one way is that as the Earth's plates move apart, the necking of the crust causes the mantle to rise. The mantle rises adiabatically, bringing its heat with it into the gap caused by that stretching. That brings the isotherm at the base of the lithosphere, about 1300 degrees, closer to the surface. So the conductivity path to the surface is less. That brings heat towards the surface. That heat causes initially an uplift, and then subsequently, as the heat is lost by dissipative cooling at the surface, it causes a contraction back down again, and that contraction enables the formation of a sedimentary basin. That sedimentary basin full of sediments, which contain water, which can store the heat, which we can then subsequently mine. So in simple terms, plate tectonics pulls the thing apart, allows the mantle to rise, puts that heat in. That heat pulse lasts about 50 million years, allows sedimentary basin formation. And this is just one way in which sedimentary basins form. And then we can tap into that heat. The mantle is made of the green stuff, peridotite, olivine, if you could see it. Most of the earth is green, rock, not cheese. And it's a conductive, at first approximation, a conductive story. I'll come back to the convective story in a minute. When we think of geothermal energy, we think straight away of Iceland, at least many people. Iceland is a specially endowed place because there you have the mid-Atlantic ridge, comes into southern Iceland on two paths, the two pink paths in this diagram, and comes out the northern end in one. And the geothermal energy projects in Iceland are shown by the red dots. Iceland, 400 megawatts electricity produced, population 300,000. So yes, a lot of the energy is produced by electricity, but on a global scale, Germany consumes about 150 gigawatts a year, I think, 150 gigawatts rate. So Iceland is relatively small, but they also produce a hell of a lot of heat. I couldn't find the figure, but knowing the Icelandic affinity with outdoor swimming pools, it must be a prodigious quantity of heat that they produce. The investment in the geothermal energy is increased with the rising energy prices, and you see the number of wells drilled has increased in recent years, and it's very much a laboratory for high temperature geothermal energy for the world. Now, Iceland is a bit anomalous because the story I told you about conduction is true as a first order approximation for much of the Earth, but we also have convective heat transfer to the surface, and that's shown in this lower diagram, where you see plumes. These are plumes of hot rock which rise from the core mantle boundary, so very deep in the Earth's interior, travel through the entire mantle and come up to the surface in specific locations. And then as the plates move over those plumes, you end up with the famous hotspot trails, so you end up with ocean island chains where you can track the movement of the plates over these plumes, which have their own reference system, geographic reference system. So it was explained to me as a young undergraduate by someone dragging a piece of paper over a lighted cigarette, and you see the burn marks as you drag the plate across. So that's good news for Iceland, but not much use to the rest of us. So this is to highlight that Iceland is an anomalous situation. Another way of reflecting on its anomalousness is that the well IDDP-1, which was drilled in 2009, has one of the more interesting daily drilling reports that I've ever read, because they drilled into magma at 2104 meters and had to abandon the well. And the wellhead temperature on that well is, last time I read it, it's kept on the web, was 400 degrees centigrade. So very close to the surface, and it was rhyolitic magma, actually, is an interesting aside, which was a bit unexpected. That was drilled in the Krafla geothermal plant, which is shown in that map, a picture in the upper left. The way the geothermal energy is generated here is that you have a hydrothermal system, so a system of fractures. They map the fractures with seismic technology, but also with gas seepage to the surface, in this case a CO2 flux, which they measure. They try and find the fractures in such a way that natural groundwater is circulating down to the top of the magma, being warmed, and can be tapped into as steam. So they essentially get steam directly from the surface from the subsurface without the need for injection. And it's a 60 megawatt plant, 230 megawatt turbines, and they had to wait for 10 years or so while an eruption played out in between the first wells and the subsequent wells. Interesting geology. Now for geothermal power, exploration risk even in places like Iceland is not zero. This was an exercise done by Stanford where they looked at the exploration risk associated with drilling for geothermal well. As an oil exploration person, I was interested in the results. About a 50% chance of success when they start, and by learning about what they're doing, they can get up to something like 80%, 60 to 80%, so not risk-free. But the recovery of power per well drilled, so the well capacity is actually very variable, as you see in the plot on the right hand side, which goes from 1 to 20 or so megawatts per well. So still room for quite a lot of geological engineering to find the sweet spots. Few places have that as a resource. Another way of tapping into the heat is so-called enhanced geothermal systems. So here you've got hot rock, essentially dry rock, so with low porosity but hot. So typically this would be a granite with high radioactivity is still relatively hot, so it's not the residual heat of a granite intrusion, but it's actually the radioactive content of the granite which is generating the heat. Granites, as you've seen in Dartmoor, nicely fractured, makes the tores, so you've got a system of fractures down there. The trick is to drill into the fractures, inject a fluid, water, and have that water take a flow path from the injector well to the producer well and extract the heat from the hot rock as it traverses between the two. So this has been tried in Cornwall many times, and in fact there's a new attempt now related to the Eden project, where a system like this is going to be tried again. Now the problem is, well, there are two problems. One is that in finding the route between the producer and the injector, you need the right degree of complexity, because if you find a short circuit where the one fracture leads from one well to the other, you don't have enough residence time to actually heat the water. It just flows from one well to another, thank you very much. Or conversely, you can not find a connection between the producer and the injector, and you pump the water in and it never comes back. So that's one series of problems. The second problem is you can induce seismicity. So by injecting the water into the rock, you're trying to crack it open. It's essentially the fracking story, in this case in a granite, and you can induce seismicity. And the famous example there is Basel in the Rheingraben, where a magnitude 4 earthquake, which is quite a big one, was induced in the city centre with an EGS project. So it kind of slows things down till people get sorted out. Shell was active in both high temperature geothermal fields and this for a while. We've now pulled out of it because of the economics and also the scale. The energy system is very, very big. EGS and high temperature geothermal is essentially a niche application. And it's a niche application, unfortunately, generally where the market, the load for the heat is relatively modest. But one thing we are doing is we're looking at fluids which might help solve this problem. So if you could design a fluid which knew whether it was in a big fracture or a little fracture, a narrow fracture or a wide fracture, then it could adjust its viscosity such that it flowed slower in the wide fractures and faster in the small fractures, and you ended up with an even front, an even flood front between the injector and the producer. So that's a shear dependent viscosity, and that's a behavior that's known. So we're doing some experiments using actually salicylates, aspirin derivatives, relatively small concentrations. They do modify the shear dependent viscosity characteristics of water. We're only 3 orders of magnitude out with the effect that we need to produce to make it real, but we keep on trying. For oil recovery using injecting water into oil fields, we have the same problem. So if we look at a categorization of geothermal resources, we've looked in this diagram of temperature versus the size of the resource on a logarithmic scale in terawatts thermal, but no numbers. We've got the high temperature supercritical steam, so that's above the critical point, which is superb, but very rare. Conventional steam, like the Krafler plant. Then we have lower temperature geothermal resources, maybe some of the enhanced geothermal, where you could use, rather than a steam turbine, something called an organic Rankine cycle. So organic in this context means a carbon-based chemical, so it has essentially a lower boiling point than water, so you can flash a liquid to a gas and use it through a turbine, but it's not water. And then you have the low enthalpy, or the low temperature geothermal energy resource, which is much, much larger. And that's what I'd like to talk about next. Oh, sorry. I'll get there. So Paris is known as the city of light, but it's also the city of heat. Paris has a relatively large and long-lived district heating scheme sourced by geothermal energy. Started off in the 60s, got into financial troubles in the 90s. They had a large sort of capital debt to pay off, got through that, and is now back on a reasonable footing thanks to the increase in energy prices. What they're doing here is supplying essentially large apartment buildings, office blocks, large institutions like hospitals with heat on a district heating scheme. And the heat comes from the Dogger aquifer, so that's the Middle Jurassic. So think of the Cotswolds, the Cotswold limestone, Great Oolite equivalent in the Paris Basin. They're mining the heat, and they mine it with a doublet. So the doublet is simply a producer and an injector, and in this case, the producer flows from the reservoir. So you're taking water, you're actually extracting hot water from the reservoir itself. You take the heat out of it at the surface, and then you re-inject that water once it's had the heat taken out of it as cold water back into the reservoir. So it's a closed loop with a pump, an electrical submersible pump in the wells. The aquifer is a depth of about 1.8 kilometers. The aquifer temperature is about 70 degrees, and they put back water at about 35 or 40 degrees. That's not ideal. It's a retrofit solution, so they're basically supplying hot water to cast iron radiators. And what you really want to be doing with a district heating scheme with relatively low temperature heat is using convective heaters or underground heaters, where you can extract more of the heat than you would through a radiator system. But they have to live with what they've got. Now, the impressive thing for me was the diagram on the left, which is a reservoir model of the Dogger interval, and the scale in between the markers on the grid is 1 kilometer. So each of those doublets is mining heat from about a square kilometer. And that's 52 years of extraction. So I think it's quite impressive. So you're getting typically 7 megawatts or so per well, the rate it comes out. Ironically, they're forced to shut in these wells in the winter period sometimes because they have baseload gas heating, which goes ahead of the geothermal, but we'll come back to that problem. It's an energy system integration problem. What they're doing is they're mining that heat, and then as the doublet reduces the local temperature down to about 40 degrees, which is the blue colours, they drill a third well, and depending upon the details of the geology, that can either be an extra producer or an extra injector, and they can keep the system going. Okay, so that's the way it works. And one point, the Paris Basin, relatively high heat flow, and a static system. So essentially the water is not flowing, which is what you want, because the water stays put. If you've got an aquifer which is busy moving water from one place to another, you've got convective heat transfer, all these nice circles would very quickly become plumes. You can see there's an interference effect beginning to be had between the wells. They are drilled deviated from single pads to reduce the footprint. They can only get so far away from each other at 1.7 kilometer depth. So why don't we do more of that? Well, this is an analysis by Professor Werner from Sweden, and he looked at the administrative areas of Europe, so that's what the little grid is, and he did an assessment of the geothermal heat at 2 kilometers, which is roughly an economic depth. If you have to drill 30 degrees centigrade per kilometer is a good rule of thumb for a geothermal gradient. So if you have to drill deeper than 2 kilometers to get 70 degrees, then you're in trouble. And what you see from this map is in southern England, Wessex Basin would be a good area. In fact, that's the jewel in the crown for UK geothermal, and has been, I think, since I was an undergraduate. It's a Southampton town hall. It's run by a district heating scheme sourced by a geothermal well from the Sherwood sandstone, and has been for some time, but that's about it. Paris Basin you see, but you see the younger basins, so the ones with more active heat flow related to recent tectonics, particularly the Pannonian Basin, Hungary, Austria, the Balkans. You see Turkey coming out on this map, and Sweden and Finland and Scotland have kind of had it with basement. Sorry guys. But so it's patchily distributed, but perhaps equally important as the source is the availability of a district heating scheme to distribute the heat to the end user. Now, geothermal's got a fantastic advantage over other forms of heating because you actually use the heat energy as heat. So you don't have the inefficiency of first generating electricity throwing away 50% of the energy, and then using a resistive heater, throwing away another 60% of the energy and having some heat. You're using heat as heat. So intellectually, it's really the right thing to do. But you do need to distribute it. And this is a really interesting map for that problem, because what you've got here on the left is a map of Europe with the distribution of district heating schemes. And you can see it's really governed by politics and the way society operates. So you see Eastern Europe. So you kind of got told how your heat was going to be delivered to you in Eastern Europe, I guess. And from what I've seen of it, you know, if you got too much, you opened a window. You know, and often there was too much. Heat was a byproduct used from industry, went into district heating schemes, and district heating schemes are very widespread. When Berlin was reunified, you had this amazing coincidence of a district heating scheme in the west, which was basically driven because it was an energy island, finding it was neighbour to a district heating scheme in the east, which was driven by heavy industry. Put the two together, you've got one of the, you know, the biggest district heating schemes in the world. Also look at Scandinavia. Again, you know, Denmark. In Copenhagen, you get a choice. You don't have to use the district heating scheme. You can heat your own house, but you will pay for the district heating scheme anyway. So it's pretty simple. So Scandinavian situations where you've got perhaps more social cohesion, perhaps a different way of viewing these problems, and Eastern Europe where you definitely had social cohesion for whatever reason, and the west of Europe substantially less. And I think that is going to be one of the main things. We're looking at business models for geothermal heat within Shell, and you know, the availability of district heating, how you trigger a district heating scheme, how you interface with the end-use customers, and the pricing, and how the market works, all big issues in getting this off the ground. The IEA has, look at Poland on that picture. Poland has actually got the second biggest square meterage of space heated by district heating schemes, not geothermal, but district heating in the world. And the world's biggest is South Korea. It's interesting. Obviously, energy in South Korea is a difficult issue as well. And America, I think, comes third, second to Poland. And China is actually moving up fast. The IEA had a look at geothermal energy, bearing in mind these problems of implementation, the availability of the resource, ability to interface with a district heating scheme. They came with a projection shown in that figure in the bottom right of around 6 exajoules by 2050 coming from geothermal energy of this sort, the low temperature sort. On top of that, they had another 6 exajoules which could come from ground source heat pumps. That's about the same again, which we'll talk about next. But 6 exajoules, if you remember the shock and awe diagram, is about 1% of the energy system. So it's really a large energy contributor. 6 exajoules is a hell of a lot of energy, but the energy system itself is very big. So other ways, ground source heat pumps. Now this is actually a renewable source because the heat you're extracting in a ground source heat pump is solar heat. So you're tapping into the couple of watts per square meter rather than the 50 milliwatts, and it is renewed. So what you're doing here is the ground is heated up by the sun, at least some of the time when we have a decent summer, and you can extract that heat with a magic trick. So you basically pump it from one place to another. So we all have a heat pump at home. All of us have got a heat pump. It's called a refrigerator. And what a refrigerator does is it takes heat from a place where you don't want it, which is next to the milk, and it puts it to the place where you don't mind having it, which is the back of the fridge. And I know this from experience because when we were first married, we lived in a residential caravan as poor students, and the heat in our bedroom was the back of the fridge, which was very welcome. So, but what a fridge basically does is it applies a trick. It's basically you run an electric pump, and the energy that goes in the pumping actually moves the heat from inside the fridge to the back, and it does that by taking the energy out in the refrigeration cycle. So basically, as you expand the gas, it gets cooler, So you can use that expansion to cool the fridge, and then when you compress it, it gets hotter. So you expand it inside the fridge, you compress it at the back where the heat comes out, and you're able to extract that heat from the space of the fridge. Ground source heat pump does exactly the same thing. So you supply heat from the soil, typically 11 degrees, 12 degrees in the UK, maybe a bit more in the south, and you take that heat, you keep that system separate through a heat exchanger, and then you run an expansion contraction system which extracts that heat and sends it to your hopefully convective heating system. You can also use it for cooling, and the way you can use it for cooling, or a way in which you can use it for cooling, are so-called absorption chillers. So what an absorption chiller does is it does that change between a liquid and a gas in a slightly clever way, so it can do it at a low temperature. Basically, you have a fluid, you have two fluids. So you start at the top of the right-hand side in the pink. You've got a so-called absorber. Start in the right-hand side with the green, sorry. So you've got an evaporator, so you've got a volatile fluid. As it evaporates, it cools, and the vapor is then taken across to the absorber and is absorbed in the absorbing fluid, and therefore becomes a liquid. So you've expanded and cooled. You then get rid of that vapor by absorbing it, so it's actually a mixture, and then you use the heat from the heat pump to re-vaporate or to re-separate the two fluids, the yellow and the purple, the green and the purple fluid, from the absorber, and you end up with the evaporator again. So you essentially have a vapor which becomes a liquid because you're mixing and demixing, and you're using the heat to do that unmixing. So this, you can therefore use your heat pumps as both heating and cooling. China is kind of leading the way in heat pump deployments. The wet soils of the Yangtze floodplain are pretty good for heat pumping. They don't use the absorption chiller mode. They just use the stable temperature of the earth to do both heating in the winter and cooling in the summer. So they essentially put the heat back. They run it in reverse in the summer and put the heat back into the soil. And they can get a pretty good balance, because if you have too many heat pumps in the shallow surface, you can actually mine the heat and start freezing the soil. So that balance, that seasonal balance, is important. And widespread urban deployment of heat pumps will be a problem in somewhere like the UK, because they will interfere with each other. Okay, so if we look at this temperature, this heating up of the soil, on the left-hand side, at the top, you see the temperature gradient through the soil due to the conductivity profile of the soil. The blue is the January one, and the red is the summer one, the June one, and you have intermediates for the equinoxes. And then in the bottom diagram, if you prefer, you can see from David Mackay's book, and if anyone hasn't read that, then strongly recommended. Free PDF download on the web. Sustainable Energy Without the Hot Air. Wonderful title. And what he's showing in that diagram is a depth of, he puts it in characteristic lengths, but it's about 10 meters depth, and he's showing the propagation of essentially the temperature wave through the soil between January and July. But if you go down to about 10 meters, it's around the same temperature all year round. So that's an ideal depth for your heat pumping operation. On the right-hand side from the BGS, we have an excellent website if you're thinking of installing a heat pump in terms of the geological peculiarities. The temperature around that depth across the UK. And what's also important for the geological considerations is the nature of the soil, specifically the water content, and that maps onto the geology. So you can recognise the geological map of the UK from this diagram. You see the Midland Valley with the sediments, you see the uplands with the impermeable soils, and you see the more porous and permeable soils of the chalk and the sandlands of East Anglia and the Wessex Basin, for example. Also, siting in terms of advection, so lateral water flow is also important for heat pumps, and then the nature of the soil in terms of digging it up, so boulder clay is kind of annoying, etc. Closer to home, very close to home, and I actually checked it out on the way here because I'd only seen the picture. Green Park Tube Station is actually cooled with a cooling system based on wells drilled either side in the park. So basically they've drilled down, they've got a cool temperature, I'm not sure the total depth, but it's a few tens of meters, I believe. And maybe someone knows the exact depth. And basically what you do here is extract the cold air, bring it across to the tube, and then above you as you walk, certainly on the Piccadilly line, you see these large convective fans which are blowing that cool air into the tube. Having delivered that cooling, the water is then re-injected in a second borehole. It's a straight through system, so it's basically produced from the aquifer, is cold, re-injected into the aquifer a distance away, and we all hopefully have a slightly more pleasant stay at the tube station. Geothermal energy, when you've got capex, capital expenditure, which is invested in a project, you really want to make it work, ideally all year round. Now, heat loads are seasonal, so one of the things we really need to look at with geothermal energy is if we can keep that capex working by using the heat all year round. Now, you can do that for cooling services, and with increasing temperatures, that may become more important. You can also, with absorption chillers, use your district heating scheme as a district cooling scheme, still sending heat round as the energy transfer medium. But it would also be neat if we could store the heat. And there are schemes for doing this. This one relates to aquifer storage. So there are a couple of projects on the books here. There's one that we're looking at in Holland, where you have geothermal doublets like in Paris. You drill those down to 2 kilometers, and then you drill into an aquifer at about 400 meters, and you store the heat that you produce in the summer when it's not needed. In the Dutch case, it goes to greenhouses as the main source of the heat, so you can produce these delicious Dutch tomatoes. They're not really delicious, by the way, but anyway, you can produce tomatoes. You store that heat and you extract it with cheaper wells. So essentially, you reduce the cost of the well stock. So you're using your deep wells all year round. You're extracting the heat, and because of that conductivity of water I told you about being so poor, the heat kind of stays where it is. So it moves a couple of meters over months, so that heat doesn't dissipate from the store, so that you can use that property to store the heat. Paris is also looking at this as a scheme. One of the system integration effects, which we're beginning to experience with the German rollout of PV, is quite interesting, because what's happening is that the PV and the wind is being dispatched into the grid ahead of other sources of power. Because if the wind is blowing, you kind of have to use the electricity. You can't store the electricity, a problem we discuss later. What that means is that the baseload gas-fired power and some of the coal-fired power is being backed out because it's not needed, which means, ironically, that the baseload heat, which is going into, for example, Berlin's district heating scheme, is not available because the power plants are cycling to accommodate the wind-to-wind delivery. So you're kind of backing out. So you're ending up with reducing the efficiency of the gas system because you're cycling the turbines, and you're ending up with a shortage of heat. So that may be a space in which geothermal could move into. Geothermal storage would really help with that kind of system balancing problem. So this is aquifer thermal energy storage. There are other systems. There are companies in the UK which are looking at tanks full of pebbles, also a way of storing heat. You can build underground or fill mine shafts with rocks. I mean, all sorts of stuff, but this is probably, aquifer storage is probably the best. Talking about storage, the main energy storage system that we currently have is the gas energy system. So batteries may come, we'll talk a bit about that, but across Europe we have a storage capacity equivalent to about 20% of the total gas consumption. So in order to buffer the gas supply against production shocks, to some extent price increases, political problems, the European Union would like to increase that number to 30%, but at the moment it's around 20% of the total annual consumption is stored. That's partly in gas fields. So my company Shell has the large Groningen gas field. In the UK we have the Rough gas field for some time offshore the North Sea, but also in salt caverns close to the demand, Salt caverns are wonderful for storage because salt is essentially impermeable. It's easy to mine. You just put fresh water down, you get salt water out, so you just extract the brine. You need to build a pipeline to a brine disposal site, conveniently the sea. But basically it's easily done. And even though salt flows, if you keep sufficient cushion gas, so you keep the pressure, the minimum pressure sufficiently constrained, the salt flowage is sufficiently reduced that you can actually cycle the container. So salt domes come close to the surface, and you can therefore drill relatively quickly, relatively cheaply, mine them and produce good storage. So that is, in Germany, related to the advance of PV and wind, an extremely active area at the moment. Let's look a little bit more about this storage problem, because gas storage is fine, but for a low carbon system, we would need to do something with that gas, maybe capture the carbon to make it a clean fuel. But it is worth bearing in mind in terms of system integration that almost certainly all that sunk investment in gas storage is going to be part of dealing with renewables intermittency. This is a complicated diagram. I'll try and talk you through it. You've got energy in power in megawatts on the left-hand side, and you've got some days in January, it happens to be January of 2008, and you've got a couple of weeks, January, February. Now, what they've done here is they've taken a segment of a power grid, which is the Vattenfall power grid in northern Germany around Hamburg, and they have taken the amount of wind energy that was generated in this period of time, and because they're looking at the consequences of a larger renewable energy source, they've multiplied it by a factor 4 from what it was in this time in 2008. And that is the blue curve. So that is the power generated by the wind turbines multiplied by 4 for a couple of weeks in 2008. Then they've taken the actual demand, so they're not envisaging demand growth in this future date, whenever it might be, and that is the red curve. So, for instance, on the 26th of January, there was a surplus of energy in this grid, and the surplus is shown by the purple, which is the difference between the blue and the red. So that's the surplus power created by the wind turbines in excess of the load for that period of time. And then the biscuit colour is the deficit that they had. Now, it wasn't actually a deficit because you have baseload power, but in the case that this was only supplied by wind, that would have been the deficit. So what we're interested in here is really, I think, the surplus, because you're generating this surplus energy to demand. The deficit you can fill in many different ways. So you've got your baseline power plant, etc., but that surplus is kind of a real shame because these wind turbines are whizzing round generating electricity, and you're actually having not to accept it to the grid because you've got nothing to do with it, which is a kind of crying shame, particularly when you're paying for it because it's subsidised. So, how do we solve that problem? Well, in Germany they have energy storage solutions, and here are 3 of them. One is called CAES, so this is the yellow box. Now CAES stands for compressed air energy storage. So a simple way of storing energy is that you compress air and then you run it back out through an impeller. So you have a compressor, you run it back out through an impeller that generates electricity through the rotary motion, and so you've got a way of recovering your energy. Well, sounds great, but actually, as you know, through expansion and compression, there's a temperature change. So every time you do that, you cool the air out and you lose energy. So it's not 100% efficient, it's about 70% efficient. Also, there are efficiency losses because you really want to have a constant pressure. So people are actually looking at compressed air in bags under the sea because then you have a constant hydrostatic load, and then you can size the compressor and the turbine for a constant pressure. And the temperature problem they're thinking of solving by squirting water with a high thermal capacity, specific heat capacity, and thereby trying to make it an isothermal process. But the point is that the yellow square is ridiculously small compared with the red. That's done in salt caverns. You would need a lot of salt caverns. I've got the actual number a bit later on in order to solve this problem. The blue is the largest, so where it says Goldistal, that's the largest pumped hydro scheme for storing energy. So in the UK we use Norwich up in Snowdon, When we've got too much electricity, we pump the water up the hill, and when we need it, we let it run back down again. And that's can be turned on very quickly, and it operates for a few hours. So that's the biggest one they've got in Germany. And if I add all of them together that they've got in Germany, that's the Sigma pumped hydro, and that's the blue rectangle. So, and it's going to be very difficult to persuade the Bavarians to put more pumped hydro storage in the beautiful Bavarian Alps. I think there are 250 permitted hydro storage sites in the Rocky Mountains, and none has actually been approved in, I think it's 20 years. So there's a major problem in terms of pumped hydro, which is the definitive solution for large-scale, cost-effective storage. So what do? Well, a solution, well, this is just the numbers. You would need 115 pumped hydro storages to deal with this problem in northern Germany in one grid with these assumptions, or 1,500 compressed air energy storage systems, or you could do it with relatively a handful of salt caverns filled with hydrogen. So if you were to electrolyze water using this spare electricity, you could generate hydrogen, you could put it in a salt cavern, and you could store it. And that's a known technology. So hydrogen has been stored in a salt cavern in Teesside by ICI for the last 30 years or so. It's a technology which is widely used in the oil industry because we need to produce hydrogen to refine oil, particularly heavy crudes. We will need more hydrogen for dealing with biofuels, and the hydrogen pipelines all over the place because of the fertilizer industry, where we in order to make fertilizer, you still have to use the Bourne Haber cycle. It's the only way, so that's ammonia plus hydrogen usage. So it's a big industry. The electrolyzers at the moment are too expensive, but Siemens and others are working hard on that problem to try and bring the cost down, and it's essentially related to fuel cell technology with PEMs, proton exchange membranes. If that technology comes off, then this could be an economic route. At the moment, it's too expensive. But there are trial projects of this ilk beginning to take place. Why is hydrogen, how does it compete with other storage? Well, the problem in storage is you need both the capacity to store large amounts of energy, and you need to be able to store it for a relatively long period of time and get it back. And really, one of the reasons why we're addicted to fossil fuels is that they have three functions: that they're an energy source, they're a fuel, which means you can take it with you and burn it, and they're a transport medium, so you can pump it through pipelines. Now, electricity is an energy source and a transport medium, but it's really difficult to store. It's very expensive to store. We are seeing a spin-off effect with the Mullers and their PV panels, because the feed-in tariffs in Germany have now been reduced to the level of below the retail electricity price. So basically, if you want to send your PV panel electricity to the grid, firstly, you can't send more than 70% of your production because they're drowning in electricity. 50% of the total German demand has been met this summer on a couple of days with renewable energy. So they're up close to 20% as a total. So people are saying, hey, which is worth saving. So you end up with prosumers who are producing and consuming electricity. Now, if that begins to take off, it may kick the price down for batteries in the way that the Mullers have kicked the price down for PV panels. But PV panels in Germany have now reached grid parity for the retail electricity price. But batteries will always be a megawatt type range. What would hydrogen, what would that look like? I have to admit here that Shell, or I guess an oil company in general, kind of likes hydrogen because it is at least a gas. So it's maybe, it is at least a molecule. So electrons, we kind of don't do electrons, but very small molecule, but it is a molecule. So we can pump it around, we can stick it underground, we know what to do with the stuff. So there's a little bit of enlightened self-interest in this. But I got our wind turbines, we got our new cheap electrolyzers because Siemens have worked their magic, or pick your favourite electronics company. We stick it underground. We probably wouldn't go back to electricity. You could, with a fuel cell, go back to electricity, but the round-trip efficiency kind of kills you. The best thing to do, having got hydrogen, would be to use it as a fuel. And that would be, you burn it and get water in a fuel cell vehicle. It's also used industrially, and over time perhaps it could displace gas for industrial heating. Hydrogen turbines already exist. You can spike it into the gas grid. In fact, my generation used to have hydrogen in the gas grid, so town gas has essentially had hydrogen. And then it was, I remember the streets being dug up and a natural gas grid coming in, which is of course pure methane. But deposits for this storage are reasonably plentifully available. We're okay in the UK. We've got Cheshire, in all the place names ending in "wich," and we've got Teesside with the Zechstein. Germany, they've got the answer to their own problem. Holland is well endowed, and then the rest of Europe perhaps less so. But this is certainly the distribution of salt allows you to do it. You can do this in stratigraphic salt. It's best to do it in salt diapirs. But you can do it in stratigraphic salt. You've got more than a couple of 100 meters. One of the projects which is currently going on is in Spindletop, which all geologists will remember, well, they won't remember, but they'll know of from the 1920s as the famous East Texas blowout, one of the biggest oil discoveries in that period of time. That sits on top of a salt dome, and Air Liquide is drilling into their two large hydrogen storage caverns. This is not for renewable energy, this is for refining. This is for dealing with heavy crudes. Because heavy crudes have a lower, higher carbon to hydrogen ratio. Okay, the next topic to move on to, having looked at storage and system integration related to that, is this issue of mineral and material scarcity related to moving to renewables. This is a periodic table, obviously. The recent concern has been about rare earth elements, which are shown here in the lanthanide series. The blue ones are the ones that the US DOE sees as critical elements. So the problem with the lanthanide element, the problem with looking at critical material shortages is not necessarily the resource to production ratio. So it's not necessarily is there enough on the earth, it's how is it distributed and where is it distributed. And actually the Geological on their flashy new website, if you haven't seen it, it's quite impressive, have got an information brief on rare earth elements. It was a hot topic, particularly a couple of years ago, when it was evident that the Chinese saw it as a strategic control point. We'll look a little bit at that later. But these, let's look at a couple of elements. I'll start off looking at lithium. The issue is not simply the resource to production ratio, how many years have we got left, but how is it distributed and how is it extracted, and is the demand, is the supply sufficiently elastic to meet the demand? So firstly, let's look at the abundances. If we look at rare earth elements in blue here, the lanthanide series, you can see they're significantly more abundant than gold. So it's not the total abundance that's the problem, it's the way they're distributed. They're chemically, geochemically extremely similar. They occur together, and extracting one from the other is a real problem. It's really difficult. The separation technology is really difficult. Also, they tend to find themselves substituting for other elements in minerals at very low concentrations. So there's really no ore to go after, and they certainly don't occur native. So you're dealing with small elements which are concentrated in geologically extremely peculiar ways. So the absolute abundance is not a problem, it's the way they're distributed. I'll move on because I'm running out of time. Lithium is basically not a problem. We use it obviously in batteries, all the mobile phones and computer batteries. Quite a large resource to production ratio. Main source is granites and pegmatites. It substitutes for sodium, and it's extracted from granites and pegmatites which have been weathered, and ideally then concentrated either by a subsurface brine or a surface brine. So what you want is a large area of granite, lots of pegmatites or an evolved granite. You want it to be ideally in a dryish climate where it can be evaporated and concentrated. So Chile wins. So the world's biggest supply is in Chile. This picture happens to be in Argentina. If we want more lithium, we can probably go and get it. Recently, the concern has been about not lithium for batteries, but rare earth elements for wind turbines. I'm not going to mention, because I don't have time, specialist elements for PV. Rare earth elements for wind turbines. Now, why do we care about rare earth elements for wind turbines? Well, the turbine blade typically goes around 20 RPM, and for an efficient generator, you'd actually kind of like 1500 RPM to use the electromagnets. And so you put in a pretty big gearbox to gear it up from 20 to 1500. And the gearbox is kind of a problem because it's got moving parts and it needs lubricating, and it's sitting out there in the sea where it gets corroded. And if it fails, you have to climb up this big thing and do something with it, and there's 200 tons on top of these poles. So you'd rather avoid the gearbox. So the way to do that is to have a permanent magnet system rather than an electromagnet, and in order to get a strong enough magnet at a reasonable weight, you use neodymium or neodymium, and you can use 50 to 60 tons of this stuff. So that would be a hefty demand. But I don't think any direct drive wind turbine is actually in commercial operation at the moment. So this is a solution which could be solved by the gearboxes if we ran out of neodymium, and we would have to just do better tribology, get the lubricants right. But that's how the issue arose. Also used for magnets in Priuses and things like that. So you use quite a lot if we go to direct drive wind turbines. 97% of the rare earth element production is in China. The resource to production ratio is very high, but the time to establish new mines is very large, partly because of the extraction problems. The price quadrupled, and there are significant environmental concerns, which I'll talk a little bit about. Okay, so these are the ores. The original ore for rare earth elements is the fractionation in rather unique igneous rocks called carbonatites. These are essentially molten limestone, so it's a lava which is a limestone. It's an igneous rock, comes from deep in the mantle, heavily fractionated, probably 2 or 3 phases of fractionation, and you also get some placer deposits related from pegmatites and so on, particularly in Australia. But the main source is carbonatites, often enhanced by supergene weathering. So weathering in the near surface, a laterite profile is really great. This is the projected demand from the USGS and the supply picture. So you can see the blue was actually the USA. That was a Mountain Pass, which was a plant that was shut down, partly because the price went down, ironically, and partly because of environmental issues. And then you see China taking over and totally dominating world demand. So these are the projected demands, and you can see already in 2012, the rest of the world is needing to add about 50% production to satisfy the demand. And that's what's got the attention. So can there be a diversification of supply? And so these projects are ongoing, but it probably take some time to get the new mines. These are mine projects which are currently responding to this demand challenge. This is a satellite photograph of the biggest rare earth plant in China. Now just look at the figures. It was opened by Deng Xiaoping with the comment, Arabia has oil, China has rare earths. It's probably a statement of strategic intent there somewhere. Significant amount of mining, waste gas, a dust concentrate. You use hydrofluoric acid, sulfur dioxide and sulfuric acid in the extraction process. You release significant amounts, you can read it there for yourselves, with every ton of ore, and it's radioactive. So the Germans have actually picked up on this, and there's now a sort of eco-movement in Germany looking at the environmental footprint of wind turbines related to where the rare earths actually come from. So you have to go through the full supply chain to understand these issues. Again, single issue doesn't really work in the integrated energy system. This is a nice picture of a carbonatite volcano. I would love to go there and see one. I never have. I wanted to say a word about carbon capture and storage, just quickly, coming to the end here. According to the IEA, in their scenario to reach 450 ppm, we would need to continue to use fossil fuels. We could not ramp up the renewables by 2050 in time to meet the demand, and we still have the transport demand. So they're looking at carbon capture and storage as a way of addressing this, and they're banking on around 20% of the carbon cleanup necessary to reach those targets coming from CCS. Now the problem is it's not happening at scale. So you can see their ramp up, and you can't see, what you can't see is at 2010 is more than a line's thickness of projects. The issue here is really the business case. Without carbon pricing, the price of the externality, this is not done. There are a number of demonstration projects being driven by different economic drivers. The one is simply that a number of fields have CO2 which needs to be extracted for the sales gas to meet spec. So that CO2 needs to be taken out and re-injected. And then you have the Sleipner project and the In Salah project in Algeria, both with Statoil, In Salah with BP, and Snøhvit in the Arctic Norway, a similar problem, also Statoil. So Statoil is really leading the way. And then you have CO2 EOR projects where CO2 is a wonder substance for enhanced oil recovery. It changes both the surface tension and the volume of the oil droplets, allows them to join together, coalesce, and flow easier through the reservoir. So you have a series of projects doing that. But there are very, very few projects purely for the cleanup of a fossil fuel resource. We're doing a couple of those. Well, we're doing one actually, which is trying to get a bid going for the Peterhead to Goldeneye project, which is CCS associated with gas power, going to Goldeneye, which is a gas field, condensate field in the North Sea. But what we really need to do is get these demo projects down so we can allay public fears about this as a technology. What happens to the CO2? Initially, you inject it as a supercritical fluid. It goes into the reservoir. It's capillary trapped, so it ends up as a two-phase system, water, CO2, and it can't flow through due to relative permeability. And then over time, it will dissolve in the formation fluid, and over longer time, it will essentially weather the mineral grains, and you end up with mineral trapping. Last point, wind. On the left-hand side, you see the wind resource doesn't have a scale, but orange is a high resource, and green is the cooler colors are a low resource. Doesn't really matter. There's enough wind if you go offshore for the resource to be adequate almost anywhere. What's the critical issue is the water depth and the connection to the grid. So it's the investment required to bring that electricity ashore, and the investment required to place the turbines in deep water. Now we're well endowed because we've got the Dogger Bank. We've got imperial designs on the Rockall Bank, but that's probably less interest, as you can see by the extension to the northwest. But we've got the Dogger Bank, which is essentially a glacial feature, tunnel valleys, moraines, and then a veneer on the surface of the sea level rise, estuarine deposits, fluvial deposits, estuarine deposits. That was at one time land, and if you want to read about it and what it was like, and what it was like for a hunter to hunt on Dogger land, then there's a book from the Birmingham group, and here's a map of what the river system might have looked like. Probably a bit over-interpreted, but it's a nice map anyway. The top end of the Dogger Bank, the planing off, the last thing that happened to it, interestingly, was a tsunami, which was caused by the collapse of the continental shelf in mid-Norway, a thing called the Storegga Slide. And that was about 3,500 cubic kilometers of continental slope, which decided that it was going to obey the law of gravity, and fell down and generated a wave, and that wave has been recorded at the red dots in northern Scotland and in Norway and dated. at least plus minus. And that essentially was the final drowning of the Doggerland and eroded some of the higher points. Now, ironically, or interestingly, for my theme of an integrated energy system, the Storegga slide sits on top of the Ormen Lange gas field, which supplies 20% of the UK's energy. So there you see the slide head wall on the left-hand side of that diagram, and in the bottom in the box you see the seismic amplitude anomaly, which is the Ormen Lange gas field. So full integration of the energy system, even through natural processes. And with that thought, I'd like to bring it to an end. Apologies for going over time. I'd be happy to take questions.
I hope you would.
Yeah.
Thank you very much. Well, who's got a few questions? Goodness me. Let's start over here. Please. Oh, here comes the microphone. Let's stand over here.
Thanks.
Ryan Law, Geothermal Engineering Limited. I'm working on some of the deep geothermal projects in the UK. Thank you for an excellent talk. It's fascinating, particularly on obviously my certain interest is the geothermal side. But you were talking about variable viscosity in fluids.
Yeah.
And I wondered, later on in the talk, you're talking about carbon capture and storage.
Yeah.
And what your views were of using CO2 as a working fluid in deep geothermal projects.
Yeah. I've heard of it, but I don't have the technical expertise to answer the question.
Okay.
I'm sorry.
That was a quick one. Right. Let's move to the centre here.
But I could connect you with people who do. Yeah, okay.
I'm a practical pessimist, but in view of the event about 2 years ago in the Gulf of Mexico, and an uncontrolled flush of oil went up, and the rest is news that most of us know. What are two examples of the worst things that can happen, both at sea and on land, in the effort to get the energy that you've described finished?
Well, I think that's a difficult one. I think, to be honest, I would have to look to the mining operations. So if I think about it, solar PV, I can't really see the danger of installing it on the roof. Wind turbines, not a problem. Geothermal energy, induced seismicity is clearly a risk, but I think it's substantially overplayed. The mining, I'm less comfortable about answering the question because it's not my industry, but I could see problems associated with groundwater pollution, health, safety associated with mining operations. And if you go to scale and you do need a lot of these difficult to access materials, you need to think very carefully about how you manage that risk. I think the oil and gas industry and the coal industry must have larger risk exposure than what I've been describing.
Thank you.
We're right at the back.
Hi, going back to geothermal energy, actually supplying electricity, I'd like to know what your thoughts are on the possibility of an electricity cable from Iceland, who've got the power to generate electricity down to the Faroes, and then obviously over to Scotland or throughout the UK offshore network.
Yeah. So I've been talking to ABB, and they've installed from the hydroelectric projects in China. They're moving 6 gigawatts through HVDC cables, and they're doing it over 2,000 kilometers. So it's onshore. But the cost that they've taken out of the cables and the thyristor stacks to go from AC to DC are impressive. And I think, their view would be that HVDC, so the transmission losses on that line are, I think, of the order of 10%. Don't quote me, but it's close to that number, which is fantastic over that distance for 6 gigawatts. Now, you'd need a hell of a lot of copper to bring that energy from Iceland, and you would need to think, or you'd need to do the calculations about the heat generation, even with those losses in the shallow sea, and what that might do to hydrate destabilization, which is probably the cause of the Storegga slide. So that's the shallow hydrate layer and soil stability related to its thawing. But I don't think that it's technically impossible. And in fact, if I remember correctly, a UK Energy Minister was over there in May, earlier this year anyway, talking to the Icelandic government about that. And while he was over there, you might also think of wind energy if you were going to do that. In fact, it might be a better bet than the geothermal, depending on how you view the landscape. Geothermal kind of looks nice with these puffs of steam gently in the background. But that's what I know about that topic. It shouldn't be dismissed. And I think, and so the Desertec initiative is essentially the same story. So the idea would be that you export solar energy from the Sahara and bring that through with HVDC cables across the Mediterranean into the southern European grid, and then supply Europe. Now, there are some problems with that. I think, the Arab Spring has kind of made people think a little bit about, do we want our power supply there? So you have to think about the long-term political stability when you do a scheme like that. But you could see, in that the energy system is integrated, which is kind of my theme, you could see displacing domestically used fossil fuels for export, and exporting the gas, which is or the diesel, which is burnt for power in the Maghreb, and having more gas and exporting the energy that way. So essentially a renewable substitution. That might also be interesting. I know the Desertec group have been looking at that as well. That's a consortium of about 90 companies basically in Germany, which is looking at that scheme as a longer term future for European energy.
No more? Well, that's good news, because... there is... no. The lady in pink. Let's do one more, and then we'll call it a day.
I would wonder about the feasibility of the hydrogen being traded, whether Iceland could become a net exporter of hydrogen and to bring it to other countries.
No, so you can, if you look deep into the future and you think about deep decarbonisation, and you think about the difficulty of getting CCS accepted in developed countries, because of the cost, because of the security fears of the containment. I mean, I think they're overblown, but we haven't demonstrated because we don't have experience in long-term CCS. So we need to get those experimental projects going. That's my plug. But you could think of a future whereby a country actually chooses to export a clean fuel and leaves the carbon where it is. So you could take Qatar, for example, or another large gas resource, and you could turn a portion of that gas or that solar energy into hydrogen, do the CCS for the gas component in place, and then ship that hydrogen. Now, we can ship liquefied natural gas, but you need to go, I think, another 70 degrees down to liquefy hydrogen. So you're talking about minus 240 or so Kelvin, don't quote me, but you need a couple more refrigeration cycles, but it's not impossible. And then you would have a premium, you'd have to pay for it, but you'd have a premium low carbon source of fuel, which could also be used as an energy transport medium. But I think we're now talking really long term.
Bruce, thank you.
Yeah.
one more thing, because I'm separated